Hi, this is Unknown Pleasures, a tiny audio visualizer experiment on my first project with WebGL and Three.js. When I first shared it on the internet, people were wondering how did I make it and how is it possible to create such visuals on the web? What are WebGL and Three.js and what exactly do they do? 3D graphics look impressive on the web. We usually see them on the award-winning websites or when some dude is doing some crazy experiment with what can be done on the browser. So it's no wonder that developers are intimidated by the subject. The terms WebGL and Three.js look alien to them and they are afraid to pick them up or go near them. But as a beginner myself, I'm gonna walk you through the world of 3D graphics on the web and show you that it's not that scary. WebGL, Three.js, and React 3 Fiber are basically layers of abstraction on top of each other. WebGL provides you the technology and the ingredients. Three.js is the pre-made recipes you can use, and React 3 Fiber is basically wrapping all in JSX tags. And it comes with a nice set of defaults, and tools, and hooks. Imagine you want to show a red triangle on the screen. The screen consists of a bunch of pixels. Is it faster to calculate the color of the first pixel, then the next, and so on? Or calculate all of them in parallel? This is why WebGL exists, to leverage the power of your GPU to rasterize pixels on your screen extremely fast. It's a JavaScript API that lives inside your browser and it talks directly to GPU through something called shader code. WebGL renders graphics on the HTML canvas element, which makes it possible to display it along other HTML elements. To draw this triangle in WebGL, you first get a canvas element with JavaScript and create a WebGL program out of it, and then create the location of the vertices and pass them to the shaders. To render each pixel, the GPU needs two shader programs, a vertex shader and a fragment shader. In the vertex shader, you return the final position of the vertex on the screen. In the fragment shader, you return how to interpolate the final color of the pixels. Each vertex is calculated in parallel and is independent of others. Shaders are written in a C-like language called GLSL. Here I return the position as it was received and set the color to the normalized RGB value of red. Here it is, a red triangle on your web page. But this isn't so exciting. I mean, yeah, you used WebGL for the first time, but where is the 3D part? Where are the delicate animations, the shapes, the models, the interactions, the lights, and the effects? Well, remember that WebGL is just a low-level browser API to paint pixels. If you want a 3D world, it's up to you to build it from scratch. Or you can let Three.js to do the magic for you, and by magic, I mean JavaScript, shaders, and math. A lot of math. There are other WebGL frameworks and libraries, but I'm going to focus on one today. Let's deconstruct a simple Three.js scene that exhibits a cube. First, our 3D world needs a physical existence, a space where everything lives inside. In Three.js, we call that a space the scene. To create our scene, we import the Three.js library and use its scene constructor. Our empty scene is missing the cube. But what's a cube really? In a 3D world, a cube is a geometric shape with a material. If we define 3 points and connect them to each other using lines, then we have made a triangle. To do that in Three.js, first we specify the coordinates for each vertex. Then we create a geometry using the Three.js buffer geometry and set those vertices as the position for our geometry. By defining vertices for 2 triangles, we can make a plane, glue together 6 planes, and now we have a cube. But luckily Three.js has built-in geometries that we can use, and these geometries hold more information than just the position of the vertices. They have normals that determine how the light should reflect when it hits the surface, and UVs that help with mapping textures. So instead of calculating all the vertices ourselves, we can use box geometry. For box geometry, we only need to provide width height, and depth. If I set all of them to 1, I basically get the same shape. Our cube is not ready yet. It needs an appearance, a way of representation. With Three.js material, we can decide how our cube will look. I choose mesh as standard material for now. Notice how Three.js supports CSS color names. All that is left to make our cube is to create a Three.js mesh by combining the geometry and the material that we have just created. We can now finally add our cube to the scene. We wouldn't see anything yet. Imagine that there is a cube in front of you in your room, and now close your eyes. What do you see? Nothing, because your eyes are closed. Similarly, in our virtual 3D world, we need an eye to see, and that eye is the camera. Without a camera, how can we know where are we looking at? Are we looking at our cube from this angle, this one, or maybe this? Adding a camera in Three.js is just as easy. We create a camera object using the perspective camera, we move it a bit from its default position, which is 0, 0, 0, and then set a location to look at. Finally, we can see nothing again. Well, because you're sitting in the dark. I'll brighten up the scene by first adding an ambient light and then a directional light, which shines on our cube from above. Our scene is ready to be rendered on our web page. We provide the Three.js WebGL renderer with a canvas element selected from our HTML page and tell it to render our scene using our camera. There you go. We can see our cube and I have no tricks left. However, what if we want to rotate our cube along the y-axis? We would need to render again. We can use request animation frame, a standard browser API which, if we call on a loop, can run the callback function that we provide roughly 60 times per second. You might not believe it, but we are done. We have made it. We have a 3D world. We have a cube, a rotating one too. Our cube can march freely and endlessly in our world. Let's add another one, maybe one more. Let's add 100 for fun. Add 1,000, 10,000, 100,000, a million. Yeah, React 3 Fiber. React 3 Fiber is a way to express Three.js in React. Organizing and composing our scene will be much easier with the help of React and React 3 Fiber. Just compare the React version of our world with what we had before. This was a lengthy introduction, yet we have barely scratched the surface. Nonetheless, now we know enough to start the Unknown Pleasures project together. After I learned Three.js basics, it was time to create something I like. I already had the idea of working on an audio visualizer in my mind. I thought it's nice because it would give me the opportunity to work with both audio and 3D animations. The iconic artwork of the Unknown Pleasures album by Joy Division and their music have always fascinated me. Bringing it live on the internet with my own style was a way for me to express this fascination and to share an experience with others, however little or short it would be. So, I had a plan, and this is how I got started. I use Vite to set up my project. With this npm command, Vite will create a React app with TypeScript and everything else configured for me out of the box. The Vite template comes with a sample content, so I delete the content and install Three.js and React 3 Fiber to get ready. I then import Canvas from the React 3 Fiber library. Everything related to Three.js should be inside this Canvas element. For convenience, I create another component to contain everything that goes inside my scene and import it here. To see something and to make sure that everything works, I simply create a box inside my scene. I can see a gray thing on the browser, but it's too tiny. I'll apply some CSS to make sure my canvas element is full screen. There it is, a gray box. It doesn't look like a box though. We are seeing a gray square. It's because we are looking at its side directly. If I change the position of my camera, you can indeed see that it's a cube. I could also rotate the cube itself, but I prefer to inspect my cube by moving my camera freely. If you go to Three.js examples, you can find something called orbit controls, which would allow you to move the camera while it will be looking at one spot. To have it in our React project, we can use the Dray library. Dray is a set of very useful helpers for React 3 Fiber. I'll install Dray and import the orbit controls from it, and add it to my scene. With this one line of code, I can now look at my box from any angle. Okay, back to the Unknown Pleasures album cover. First things first, let's change the background color of our scene to match the album cover. For that, I use the color element and I attach it to the scene background. In React Fiber, the attach keyword means this is the property that should be set, so this will set the background property of my scene to this color. Now the lines. I went looking on the Three.js documentation and I found that there is a line object that I can use. So I create a new file for my lines component and add my line object, which needs a buffer geometry and a line basic material. If you recall the previous section, you know that buffer geometry means that I should define the geometry myself. For that, I need a direct access to my line object, and this is where React's reference feature comes handy. We are going to work with references a lot from now on, so get yourself comfortable with them. What is a line geometry? Well, a line is when you connect two points. I can have as many points as I want to make more lines, but for me 2 points should be good enough. I'll go from -1 to +1 in x-axis, so if my math is correct, my line should be 2 units long along the x-axis. My line is here, but he's lonely out in the void by himself, so before his unwanted thoughts make him go insane, I'll add more lines. I'll do that by choosing a number and make an empty array list of that count. With React's use memo, I'll make sure that no new array is created on every React DOM's re-render and make sure that I'll always get the same array. Then I simply loop through my list and create a line for each. I group my lines by creating a Three.js group and assign the ref to that group instead. So now I need to go back and create points for each line. Since I set the ref to the group, I can access each line by looping through the group's children. I still see only one line, and that's because all my lines have the same position. So I move them along the z-axis by setting the position z to a value based on their index. I'll divide it by some number to bring the lines closer to each other. You'll notice that the lines are not exactly centered on my screen, so I also move the whole group based on the gap between the lines to make sure it's centered. Let's take a closer look at the lines. They are too thin compared to the lines of the album cover. If I check the Three.js documentation for line basic material, I can find the line width option to set its thickness. I set it to 5, but I don't see a change. I set it to 10, 50, still nothing. Back to the documentation again and scroll down a bit and notice that it's actually gonna be 1 regardless of what I set it to. So I can't use lines because I can't change their thickness. Well, I have to give up. Three.js wasn't for me after all. The idea was stupid anyway. Who wants to look at music visualization? It's not Winamp and it's not 2001. I should have stuck to CSS. I'm not even good at that too. No wonder I don't have a job. I should have. Wait, rewind to the box. What if I shape my box like a line? What if I increase its width and reduce its height and depth? Now this looks like a line from the album cover. Let's make more. I got rid from most of the code since I don't need to define my own custom geometry. Also, instead of manually centering my lines, I used the raise center component and let it handle it for me. My lines are as flat as they can be. Looking closely at the artwork again, I can see that I need to add curves that elevate and peak around the center of each line. If I find certain vertices in my line and change their position, I can achieve what I want. But how do I know where my vertices are? And how many of them do I have? To find out, let's pick one line and resize it for a moment. I'll make it a 3x1x1 box. Three.js allows you to look inside your geometry by activating the wireframe on the material. It's apparent now that each surface consists of 4 vertices and 2 triangles. In addition to width, height, and depth, I can also set the number of segments for each of them. A segment is 2 triangles that make a rectangular face. So if I set a high number for my width segments and keep others at 1 because I only care about the width, I can see that I have more vertices to work with. Now it's time to control these vertices using shaders. I can change mesh basic material to shader material and provide my own vertex and fragment shaders. Three.js expects a string for the shader programs. Remember that shaders are written in GLSL. A shader requires a main function that assigns a value to a specific variable for that shader. Let's focus on the fragment shader first. In the fragment shader, I need to assign the color of the pixel to GL_frag color. The color should be in RGBA, where each of the red, green, blue, and alpha channels range from 0 to 1. So if I set all of them to 1, my box will be white. I don't want it to be the whitest white though, so I reduce the brightness by a tiny amount. Vertex shader, on the other hand, needs the final position of the vertex assigned to GL_position. If I leave my function empty, my box would be gone because WebGL won't know where to render it. To calculate the position, I need the help of Three.js. Take this model for example. Three.js gives me the local position of each vertex of my model relative to its origin. It also gives me matrices that would help me to transform this position into its right place on the screen. If I multiply the position by the model matrix, I'll position my model in the world. If I multiply that by the view matrix, I'll transform it according to my camera. And if I multiply that by projection matrix, I'll get the part of my model that should be visible on my screen. So I do exactly that, and indeed I can see my box again. Let me do a quick cleanup. I created separate files for each of my shaders, but importing them won't just work, because if it did, the life would have been too easy. I installed the plugin for Vite to handle GLSL files and also told TypeScript how to react when it sees one. But why did I do all of this? Oh yeah, I wanted to add waves to my line. Here is a simple wave. It's called the sine wave, and this is its mathematical formula. It repeats forever and it has amplitude and frequency. Amplitude determines the maximum distance of the vertical value from the center, and frequency determines how often a complete cycle happens in 1 unit of time. I can decrease the amplitude by dividing the sine value in half, and increase frequency by multiplying x by 4. I can add waves to my line the same way. For every vertex, I'll add the sine value of its x to its y. Isn't it cool that how this was done with only one line of code? I bring the rest and reshape them back into line again, and then make them even more wavy. Something is not quite right. These are supposed to be signals received from the outer space, so how could they all be the same? I need randomness, and not random randomness, but a pseudo-randomness called Perlin noise. If I use completely random numbers, my vertices would jump. I want something smooth, where numbers seem random but are continuous. With the Perlin noise function, I can pass the x position as the input value and receive pseudo-random y values that are continuous. There are different types of Perlin noises that I can use. I'll go with this classic two-dimensional Perlin noise. I put it in a file in my project and import it in my vertex shader. Now I just replace the sine function with the noise 2D function. The second dimension is for time to animate my lines, but I leave it at 0 because that's for later. I'll play with the frequency and the amplitude to find what I like. The waves look more natural now, but every line repeats the same wave. To have different waves, I can add custom offset to each line. With uniforms, I can pass down information to my shaders, and by using the index of the line multiplied by some random number, I can achieve a unique offset value for each of my lines. This would work, but it would cause me problems in the future because I'm passing a new uniform object each time React re-renders my component. I'll move the individual line to its own component and use React's useMemo to make sure I'll always have the same uniform object. Now I define my offset uniform in my vertex shader and then use it to offset the x position of my wave. Nice, we are getting very close. It's time to add the bigger waves. I can add waves on top of each other, so I basically copy my current wave and set the amplitude of the new wave to a bigger number and its frequency to a smaller number. My new wave is everywhere, but I only need it at the center of my lines. For each face of my line, I have access to the UV coordinates. UVs are two-dimensional coordinates that range from 0 to 1. They are useful for many things, but I'll use them to find the center of my line. So for every x in my UV, I calculate its distance from the center and multiply the amplitude of my wave with that value. Now the center is flat and the edges have the maximum height of the wave. I wrap it in the absolute function to make sure I'll always get back non-negative values. I also want my values to range from 0 to 1, so I multiply the result by 2. I should reverse everything, which means have the maximum height at the center and the flatness on the edges, so I subtract the final value from 1. I can extend the flat portion by applying the wave exponentially, so I raise my value to the power of some number. And I'll do the same for my wave itself to slightly increase the intensity of the wave at the center. The new waves are too smooth compared to what it is in the album artwork. I can add a bit of roughness by applying another layer of small waves at the center. Also notice how I can see through the waves, but that's not the case for the album cover. I'll use a trick by putting a plane under each line and coloring the plane the same color as the background. I create another mesh with the same Z position as the line, but use the plane geometry this time and place the plane under the line. Actually, now that I'm here, let me move the creation of geometries to the outside of my React component. Having one geometry instead of dozens would improve the performance noticeably. Let's see what happens if I use shader material and pass the same vertex shader I used for my line. Pretty cool, isn't it? I just need to change the plane's color now. So I make a new fragment shader file and set the color to the normalized RGB value of my background color. You know what makes it cooler? Animating the waves. Remember the second dimension of the noise, which is currently set to 0? I will replace it with the amount of time passed from the Big Bang of my scene. First, I group my meshes. Then I import React 3 Fibers useFrame, a React hook that runs your function on each frame and also gives you a bunch of data to work with. One of them is to get the elapsed time, so I use that to pass the time to my lines using uniforms. I should make sure that my time uniform has a default value. Now I use the time uniform to continuously update the waves on each frame. Whoa, this is chaotic. Let me slow down the change of time. Better. Okay, one final touch, I promise. Notice how in this Three.js fog example, the hills far away from the camera are faded and are less clear. I want that, so according to the documentation, I add the fog to my scene, but it won't take effect. Why? Well, I have written my own shaders, so I should handle the fogs manually. With some search, I found out that I can include the code that Three.js uses. I need to make sure that I've also added Three.js specific uniforms for the fog, and that the fog is enabled on my both shaders. And now, I can enjoy the fog that I have given. I can keep refining what I have, but I'm happy with the current result. Music turns the fleeting moments of our lives into memories before they vanish forever, and summons what was thought to be forgotten. It rises above the unexplained, and it brings meaning to our solitude. So how can I add this magical thing to my website? Well, first I put the track inside my projects folder, then I create a file for my audio component. Here I import the positional audio from Dre, and for the audio I give it the path of my audio file. That's it, I now have music in my project. You are not hearing it though, that's because it's not playing. To interact with the music, I'll add a button. I create the button, add it to my app, and I style it. Nothing fancy, just ordinary CSS and HTML. When I click on this button, I should play the music. That means that my button should communicate with the audio component. There are a lot of ways to do this. One way is to share states between them. To make things easy, I'll install a simple state management library called Zustand. It's from the guys who made React 3 Fiber. My global store is going to be minimal. One field to track if music is playing and one to update that field. In my button component, I set the music state to playing for when I click on the button. And in my audio component, I can watch the music state. To play music, I need a direct access to my audio component. I'll accomplish that with React's useRef again. Now I can simply play or stop the audio based on what my music state is. Let's try it. Did you hear it? To perceive it better, let me visualize it with the lines. That's the main goal of this project anyway. I have the individual lines and I have the music. I need some kind of data that can be mapped to these lines. This data is the frequencies of the audio spectrum at each specific point of time. Browsers have an API that analyzes the audio for you and gives you this information. I'm gonna use the Three.js version, which is called Audio Analyzer. It accepts an audio and a number for the frequency domain. It doesn't have much use in this file, so I move the creation of the ref to the outside of the component and export it from here. To then import it in my lines file. Here I can inspect what sort of frequency data I receive when I play the song. It turns out it's an array of numbers between 0 and 255. I can use this number to decide how high the waves should be for each line. So I get the frequency for each line based on their index number. It ranges from 0 to 255. I can map it to be between 0 and 1 using a map function. I can use this number in my vertex shader to control the amplitude of my wave. So I create a strength uniform, and in vertex shader I simply multiply the amplitude by the strength value. Nice. But notice how the movement of the waves is harsh. It's because the strength is jumping from one value to another. However, if I find points between them and change their strength gradually, I would see a smooth animation. This is called linear interpolation, or LERP for short. There are nonlinear variations like cubic Bezier, where you have curves instead of a straight line. LERP should be good enough for me. There is no native LERP function, so I add my own. I have the current strength and the next strength. I decide how much closer it should get to the next strength each time. 0.25 basically means 25%. Looks smoother now. One more thing I want to do is to fade out the button when I click on it. I can do it with CSS or plain JavaScript, but later I have to deal with a lot of animations. So why not just start using an animation library now? GSAP is a popular choice when you are working with Three.js because it's simple to use and has a nice set of features that go along well with Three.js. So I go ahead and add it to my project. I expand the onClick handler to add the GSAP animation. I specify the target element, which is my button, the property I want to animate, which is opacity, and how long the animation should take in seconds, which I set to 1. Only when the animation is complete, I start the music. I also make sure to remove the button after it's faded out. What should I do now? Answering this question is the hardest part. Sometimes it would take me hours just to come up with an idea. Being able to quickly modify the properties of my objects helps me create what I like a lot faster. A tweak panel is particularly useful for this purpose. I can play with the strength of the waves, increase or decrease the gap between them, or adjust their scale. The options are limitless. I can make my own tweak panel or use one that someone else has already made, which is more convenient. There are quite a few options. I pick Leva. I basically do the same in Leva. After trying out different settings and positions, I find the state that I like and animate my scene towards that state. For example, I decided that once the song has started playing, I should move the camera slowly down and then expand the lines and move the camera again. To write this in code, I create a custom React hook to have some space and clarity. I grab my camera from the React 3 fibers use 3 hook and use GSAP to update its position slowly and with a slight delay. The ease is set to none because I want a linear movement for my camera with no accelerations. Excellent. Next, I want the lines to expand. When the camera movement has finished, I increase the Z position of each line based on their index and the gap number. Then I move the camera along with the last line. Nice. Looks almost how I wanted. The fog seems too strong. I weaken its power. I would also like to surf above the lines next, so I tell the camera to move back to where it came from, but this time more slowly and gently. Now let's see what we have got. Not bad. I'm gonna stop here though. I could keep on exploring even the smallest details, but I wouldn't uncover anything new. You already know how to use Three.js, how to create objects, place them on the world, and animate them. So how I made the original Unknown Pleasures project shouldn't remain a mystery to you anymore. Still, you might see things from the project that question your ability to do them. To leave nothing unmentioned and to have a quiet night's sleep with no guilty conscience, let me go over them quickly. First thing you notice is how the lines are bent. It almost resembles a road. Look what happens if I offset the x position of each line by a small amount based on their index. This is a straight line. Raising it to a power gives me a curve. I want a curve the other way around, so I reverse my index. Applying a similar curve with the y position is a poor guy's attempt to achieve the cinematic effect he saw on the movie Inception. Moving on to the next stage, the lines get turned into strings hanging from above. A quick glance at the line's vertex shader reveals that there are still numbers that can be altered to transform the shape of the lines. When I replace the power number with a uniform and then tweak the current values and position the camera at the right spot, you would see how new pictures emerge from different set of configurations. Shortly after, the texts start appearing. These are HTML texts, each coordinated with a specific Three.js objects. Let's say I want to attach a text to the third line. I import the HTML helper from Dray and use it to create a paragraph. I apply CSS styles and place it on my desired location. Once ready, I hide it to make it visible again when the time comes. Here comes the moon and the stars. The moon is a big white sphere resting in the back, and stars are points, many of them, scattered across the scene, neighboring the moon. How are they scattered? Random x, y, and z position. How are they glowing? Each point is a rectangle, so I use shader material, where I can use the distance from the center as a measurement for the white color's strength. Finally, and most importantly, how did I sync everything with the music? The answer is simple. I played the song again and again and again and again. I must have repeated thousands of times, days and nights, just to get the exact time right. I can still hear the song in my head. It's already a long video and I cannot fit everything in one, so here are things you can go and explore on your own. See what different type of geometries are ready to use in Three.js and how can you create your own. I mostly used Mesh Basic material and Shader material, but there are more. For example, Mesh Toon material gives you a cartoony look. There are different type of lights you can add to your scene. Shadows are supposed to be enabled separately. Beware of the performance. With post-processing, you can add effects to the whole rendered image. Think of it as something like filters that you apply to your photos or videos. Learn about textures, how to load 3D models. Maybe you even want to create 3D models. In that case, look into softwares like Blender. Shaders are extremely powerful. They are the bare bones of graphics programming. The book of shaders will be a good start to put you on your path. I never stop being surprised by what others create with mere shaders and math. Get comfortable with linear algebra, learn about Cartesian coordinate system, master vectors, recollect trigonometry rules. Know enough of matrices to have an idea of what's behind transformations. 3 Blue 1 Brown has a wonderful series on the essence of linear algebra. Animations breathe life into your scene, and doing them right is the difference between night and day. Use Disney's 12 principles of animation as your basic starter guide. And finally, my favorite one, creative coding, a term that contains all the creative things that people can do with code, from generative art and music to artificial intelligence. Daniel Schiffman's channel Coding Train is a fantastic inspiration, and his book The Nature of Code is a beautiful gateway into creative coding. This is it, it's your turn now. Go ahead and create something amazing, and hey, don't forget to share it with me.